Okay, we start today's session, and the first speaker is Schiro. Welcome.
Thank you very much, Misha, and thanks the organizer for inviting me and for putting together this program. It's a pleasure to. Sorry, I need to cancel this meeting being recorded. Okay, so the topic of my talk, since the workshop is about impurities, I thought of presenting some new results about quantum impurity physics, hopefully in a context that is a bit different from what usually you have seen, and maybe this can stimulate a little bit of discussion. So this will be about impurities coupled to Markovian and non-Markovian environments, and I will try to define everything throughout the talk. So the outline, so I will start as gently as possible, trying to present what I think are two paradigms, 2 points of view of open quantum system that you might have been familiar with depending on your background, quantum impurity models on one end and Markovian quantum system on the other. I will introduce them and give some motivation and some example, and then I will enter in the main part of the talk in which I want to convince you that those two paradigms can actually be bridged together, introducing what I would call Markovian quantum impurity models. And I will give you examples from my own group and other groups of problems of this sort, motivation, and somehow ways of addressing and solving those problems. And then I will give you some practical examples, some application that will be mostly fermionic and mostly bosonic Markovian impurities. And I will be more precise on that in a little bit. So let me start by saying the concept of open quantum system is very general and very broad depending on the discipline. So when I usually give a talk, I try to clarify as much as possible what I mean and what is meant by open quantum system, because depending on whether you're a condensed matter theorist or a AMO person or a statistical physicist, you might have a different perspective. So the general system that I will have in mind is typically a small system, small quantum system. You can think of a two-level system, which is coupled to an environment. Okay, and this environment is described by a set of degrees of freedom of the bath. And this kind of system bath picture emerge, as I said, in various contexts: impurity in metals and quantum dots in more like condensed matter, but also photons in a cavity or atoms under spontaneous decay or qubits and so on. And the key point that one needs to realize is that the dynamics of the system is strongly affected by the bath that induce some retardation and some memory. And what is really important is to distinguish what kind of environment you are embedding your quantum system in. And I will somehow loosely speaking refer to slow and fast bath. On the left-hand side, you see what is a slow bath kind of spectral function. So this is the distribution of the frequency mode of the bath. And for people in condensed matter physics interested in equilibrium problem, this is the typical form that you find, for example, in Caldera-Leggett, if the bath is made by, for example, phonons, some power low and low frequency. And one typically is interested in the low frequency behavior of the bath, and that's somehow what control and has more effect on the physics. On the other hand, you might think of systems which are driven at some finite frequency, and so and you're actually interested in the spectral function of the bath around the carrier frequency, and in that sense we can call those baths as fast bath, and this is what I will refer to Markovian open system. So let me give you a little bit more of example and insight on these two paradigm, and then in a little bit I will try to merge these two concepts. So quantum impurity physics, that's how I bumped into it in the first place. The effect of dilute magnetic impurities in metal and the Kunda effect. This is a very old problem. the dense amount appeared in many contexts over the years. So over there, you see the resistivity of a metal as a function of temperature that has a strange minimum, and this was somehow rationalized by Kunda. And the same kind of physics shows up in transport experiments with quantum dots and molecules embedded in leads. And there are now more and more experiments on this kind of setup. For example, light control of quantum dots. You can have impurity in cold atomic gases that kind of incarnate and realize this physics. The kind of standard textbook model for quantum impurity physics, at least this is my personal point of view, is what is called the Anderson impurity model. And you see the structure of this Hamiltonian will sort of repeat throughout this talk. You have some quantum degrees of freedom. Here is a fermionic level which can be occupied by a spin up or a spin down, a doubly occupied side or an empty side, which is coupled to a set of free fermions. And this model has been introduced and studied and understood by now since a long time as interesting physics. As you kind of lower the temperature from very high temperature, there are different energy scale in the problem. You see when temperature is of the order of the Coulomb interaction, the charge fluctuation on the dot start to be quenched, and they cost energy to have multiple occupancy. And you enter in a regime in which the charge is frozen and you only have the spin. And the spin can still fluctuate until you reach a temperature that is exponentially small in the interaction, is the Kondo temperature, which is the temperature below which this fermionic environment start to play a major role and screen the spin, creating a collective many-body state between the spin of the impurity and the bath. And you have a picture on the right side taken from quantum dot physics. And this kind of Kondo effect shows up in many experimental probes. And one famous experiment was the conductance as a function of the gate voltage. And you see that essentially, depending on whether you are even or odd occupied, you can either have unitary limit of conductance, so the maximum available channel for transmission, or have a very low conductance. And the understanding of that is that there is a collective many-body state that is available for resonant transport. And this is, I would say, one of the most understood impurity problem. And also, from my point of view, it's sort of a paradigm for strongly correlated electron. First of all, because it's very rich, but rather simple and understood. And also from the point of view that field theory, which I will introduce later on, this kind of impurity model play an important role. On the other hand, so let me just add, one comment. So this kind of impurity model is a genuine many-body problem because you have the impurity, which by itself is just a small quantum system, and you could diagonalize it easily. But you have the bath, you have the bath degrees of freedom that actually play an important role in this Kondo physics. So you have a many-body problem, genuine many-body problem. On the other hand, there are systems in which the dynamics of the bath is sufficiently fast that you can actually write down for your system of interest an equation of motion for the density matrix that enjoy two very important properties. It's local in time and it's linear in the density matrix. And this master equation can be taken in the Limblad form, which is written over there. You have two terms. You see a coherent unitary evolution, which is nothing but the standard von Neumann equation for the density matrix. And you have what is called a dissipator, where a set of jump operators describe the effect of the environment on your system. You see that this equation, as I said, is local in time. So it only appears the state of the system at time t. This is a statement about the so-called Markovian approximation. And it's linear in the density matrix. You see that you have density matrix on the left-hand side, on the right-hand side. And this is a statement about a Born approximation or weak coupling approximation. In fact, this master equation you can derive under several assumptions and textbook of open quantum system. So this, of course, is an idealization. You are disregarding memory effect. You are disregarding memory effect from the environment, and you are disregarding system bath entanglement. you are essentially saying that the environment is affecting the system through this jump operators, but the system is not kind of feeding back any effect on the environment itself. Nevertheless, it's a very useful, I'll try to convince it's a very useful idealization. First of all, because it allows sort of theoretical insights and because it's experimentally relevant. Let me just mention that, so since we start working on this, I've been for a long time trying to derive diagrammatically this linear master equation, and it's something we succeeded to do only very recently. And so I'm flashing this. If someone is interested, I would be happy to enter in the details, but that's not really the topic of today. So what are kind of theoretical insights we can draw from this? You see, this is a linear equation, and it takes some sort of formal similarity with Schrödinger equation. So it's a linear equation in terms of a super operator, which is an object that takes density matrix and map into density matrix. It's called Lagrangian. And so it's a linear equation. You can, it's a well-defined dynamical map, has nice properties from a mathematical point of view. Basically, you are sure that if you start with the density matrix that is a positive object, you continue all throughout the evolution to remain positive to the well-defined density matrix. That's not always the case. And the fact that there is a Lagrangian, which is an operator, it's a linear equation, suggests that you can diagonalize this Lagrangian a little bit like you would diagonalize your Hamiltonian. And diagonalizing this Lagrangian, you get modes, and there are very nice properties. First of all, for finite size system, this Lagrangian admits a zero mode, which is the stationary state of the system, and this is guaranteed by the structure of the linear master equation for finite size system, as long as you don't have sort of strong symmetries or integrabilities. And then you get another set of eigenmodes and eigenvalues. These eigenvalues are complex because this Lindblad superoperator, if you think about it as a matrix, is a non-Hermitian matrix. So there are complex eigenvalues which describe decay modes. These eigenvalues have a real and imaginary part. The real part is negative, such that you describe damping, and this is also guaranteed by the form of the Lindblad master equation. So you have these decay modes and a stationary state. And the interesting thing is that this, depending on the form of the jump operator and dissipator, you can arrange stationary state for the open quantum system that are very far from being thermal. Okay, so you not necessarily thermalize to the thermal equilibrium described by the unitary part of the evolution. So where this kind of system pops up, there are a variety of contexts. I'm usually interested in system in cavities, atoms and photons trapped into cavities, either optical cavities or solid state architectures, either on, let's say, small system like single qubit coupled to a cavity mode, or many body incarnation of that you have on the right hand side in this kind of sketch that describes an array of coupled cavities. So these are systems that are used to describe light matter interaction at the quantum level. And a very important point is that the system, which involves photons, are open in the very sense of the term. There is leakage. Photons can leak out of the cavity, and so they typically need to be refilled. And this set up sort of non-equilibrium stationary state due to quantum losses. Something that is very important for me to stress is that these dissipative processes that I will define and give an example in a second, this jump operator, are highly tunable. You can think of them as not only single particle losses, but I'll give you an example, can be even more interesting kind of process. So for example, the simplest thing you can have in mind, if I take an example from cavity PVD, is just decay of an atom from an excited state, or the photon loss process, single particle photon loss. So you see, this is described by a master equation where the dissipator, you have a jump operator that is just the distraction, annihilation operator of the photon. And on the other hand, you have a spin flip operator that brings the atom from the excited state to the ground state. Okay, so these are the simplest kind of dissipative process that you might think. And in order to see interesting physics for cavity QED, you typically want to be in a regime in which the light matter coupling is much stronger than those losses, so that there is entanglement between the photon and the qubit. But that's not the end of the story. For example, and there is actually a field trying to design jump operator in order to achieve a certain target state. This is called dissipation engineering and starts from quantum information up to many-body physics. Here I'm putting an example from NAS, Zaki Lekta's group, where they managed to arrange this kind of dissipative process that you see over there. The dissipator involves the destruction of two photons. So these are two body losses. And you see immediately that two body losses is a correlated dissipative process. You need to have two photons on the same side in order to decay. So they need to know what the other are doing. So it's already start to beat many bonds. And this is actually was used for creating cut states that are very robust to the coherence. And this is something that for quantum information, obviously, is very interesting, but as I will discuss later, also interesting somehow consequences, for example, for quantum simulation. So this is something that we'll see a lot later in this talk, the role of these two body losses in the problem. Other platforms are also amenable to this kind of dissipative processes, for example, ultra-cold atoms, which of course are the ideal platform for quantum simulation, for dynamics of isolated system. Let's say almost isolated system, also cold atoms have some sort of dissipation on some maybe long time scale, but this dissipation process can also be highly tunable, and I'm giving two examples that also are interesting. For example, you might have heating due to spontaneous emission, and this gives rise to a dissipator in which essentially the density of atoms on a given site act as a jump operator. And again, you see that this jump operator results in a sort of interaction. If you think of Hamiltonian, you see this dissipator now is not anymore a single particle operator, but it's a sort of interaction term. And again, also in cold atoms, you can actually realize through inelastic scattering these two body losses. This is exactly the same dissipator that I showed you before. And there were experiments that, for example, explored the role of these two body losses on the Bose-Hubbard, the standard, let's say, dynamical crossover between Mott insulator and superfluid that has been somehow studied since more than 20 years, and the effect of this dissipation to this kind of dynamical process. And I will go back to it to present some of our results in this course. So I gave you these 2 points of views, and hopefully you can find yourself either in one set or in another one. The aim of this talk is try to convince you that actually we can merge these two. There are platforms that operates in a regime in which actually makes sense to think about both kind of environment. And I want to present a sort of schematic setup of a Markovian quantum impurity, which means that I have a small system that it's my impurity system, which contains some interacting quantum degrees of freedom, but there are few degrees of freedom, can be a single quantum spin, a single fermionic level. And this is coupled to a non-Markovian bath, which means that it's a frequency-dependent bath that contains a lot of modes, and these modes play a role, often out of equilibrium. And here I'm saying that this is out of equilibrium. So non-Markovian here, first of all, means frequency-dependent. There is a frequency-dependent because it means that it's memory due to the bath. And you see here I'm using two correlation functions because this means that the system is out of equilibrium. If you would be in thermal equilibrium, these two correlation functions would be related by something very general that is called fluctuation dissipation theorem. And when you are in a generic out of equilibrium condition, you need to specify the spectrum of the bath and the occupation of the bath. They are not given by the same function just because the density matrix of the bath is not the Boltzmann wave, because you are in an out of equilibrium state. So you have this non-Markovian bath, and then you have a Markovian environment that is described by some local, or possibly non-linear jump operators, and described by a local Limb-Blanc. Okay. So let me give you some practical example of this sort of scheme, and this is something that people have started to look very recently. I will give you 3 examples. The third one will be really relevant for my talk, but I want to present a little bit more broadly what this problem is about. So if you're familiar with the Kunda effect, that is essentially what I introduced at the beginning of this talk. Well, you are interested in this story, you might want to read this paper by the Ueda group in Physical Review Letters in 2018, which was motivated actually by an experiment, called Atom experiment, where these inelastic two-body losses that I was mentioning were actually playing a role. So here you have a spin, a quantum spin, SU2 quantum spin that is coupled to a fermionic bath. So in the experiment, this would be essentially two bands, one delocalized band and one very localized sort of impurity. And the coupling between this impurity and the bath is a sort of antiferromagnetic exchange that you see over there, as usual in quantum physics. The spin of the impurity interacts with the spin of the bath at the site of the impurity. But then because of this inelastic two-body collision, you have the jump operator of this form that I write there, I try to describe. You see, these are processes in which you can destroy a fermion from the bath with spin down and a fermion of the impurity with spin up. And so again, these are correlated processes. And when you put them into a master equation, they give you essentially a Markovian quantum impurity model, a Markovian Kunda problem, which in this paper they map into a non-Hermitian version of the Kunda problem and found very unusual properties, in particular very unusual RG flow and some interesting physics that I'm not going to enter in detail, but this should be just serve as a motivational sort of kind of system you can have in mind. Another example, again motivated by a Atom experiment and studied by a group of Sebastian Dill, is also very simple. You have a sort of one-dimensional wire where you have fermions, for example, and you have a localized loss. So there is a site in the system in which your atoms can kind of escape. You see, this is described by what? Described by an Hamiltonian, described just 1D fermions, a master equation where you have now single particle losses, but you see the single particle losses, you see on the right-hand side, they are just localized at one side. Okay, so if those are familiar with impurity in Lattinger liquids and Kane-Fisher problem, this could sound somehow similar. In that case, it's a problem of a single potential barrier where electrons can kind of scatter off. And here it's not a potential barrier, but it's like a depletion. And you can imagine that what happens is that those fermions kind of leak out from the hole. But since the system is macroscopic and your hole is order 1 over the volume, you create a stationary state. It doesn't deplete right away, right? It creates a stationary state, you see it here, which is a current carrying stationary state. There is a finite value of current before actually depletion happens. And you see that eventually this system will go to the vacuum, but on a time scale, the scale with system size, you have some finite current to it. The system is out of equilibrium. And those guys found some interesting scaling of the probability of escape from the system, which actually, surprisingly, goes as 1 over the dissipation. You might think that the better the dissipation, the bigger the dissipation, the more the probability to escape. Somehow this is true at small dissipation, but at strong dissipation, actually goes the other way around. This is a signature of what is called quantum Zeno effect, and I will go back to it, but just again, sort of motivation of kind of, and again, you can think of it as the entire system being the sort of non-Markovian bath, and the localized dissipative impurity as the Markovian aspect of the problem. So what I will tell you more in this talk is a model that we can call bosonic Anderson impurity model. So you have essentially an harmonic oscillator or a single side Bose-Hubbard. You have boson on a side. You have to pay energy U to have multiple occupation. And you have a coupling to a Markovian bath that is described by a set of harmonic degrees of freedom. And you have a set of jump operator that I will that describe essentially 2 processes. Pump, which is adding particle, and this is the first set of dissipator. You create a boson with a given array, and 2 body losses that I introduced before. So you see, you have to have 2 bosons on the same site in order to dissipate those particles. You can think of that as a model for circuit QED experiment. If you have in mind this let us set up, or, for example, an atomic impurity in a DC if you are able to engineer this in elastic collision. For me, this has some theoretical interest in the model itself, but I also want to say that this is sort of very much like in equilibrium. This is a paradigm for the physics of open quantum many-body system. This can be formalized, and I'm just adding this slide here by a recent work where we've shown that if you think of a lattice of this dissipative object, so you have a lattice where on each side you have this dissipator, you can map this problem in the large connectivity limited through something that is called dynamic field theory exactly onto a Markovian quantum impurity model, which is now embedded in a self-consistent field. So this is to say that there are, for me, two reasons to look into this Markovian quantum impurities. On one hand, they are interesting and simple, but non-trivial many-body problems, and they can give you insight on much more challenging extended many-body system through dynamical field theory. Okay, so this, I hope this was enough in terms of motivation. Let me say a little bit how we can solve, and we could solve this Markovian quantum impurity model. And let me first of all stress that this is a challenge because many of the methods that we use to solve impurity problems do not naturally extend to this Markovian setting. For example, you might be familiar with quantum Monte Carlo, which usually suffer from sign problem when it involves dynamics and real-time evolution, although there have been a lot of developments in the past years, but it doesn't naturally apply to the system. And that's the same for numerical renormalization group or for matrix for state. And the challenge comes from the fact that you have to deal with two things. You have to deal with this non-Markovian bus, which induced memory requires many modes to be captured. And at the same time, this Markovian dissipation, which can be actually more sort of an interaction than a single particle process, the sort of dissipative interaction. Because of, for example, these two-body processes in which two photons escape from the system only when they are two on the same side. This is a correlated process and requires some sort of many-body technique to address.
May I ask the question of absolutely kind of ignorant person? I apologize. It's very probably bad question. I thought that indeed Markovian bus means simplification over non-Markovian. I don't understand how you are saying what is Markovian means that you don't care about preceding time steps. Non-Markovian, you care about preceding time steps. It seems that if you can forget about the necessity to know initial time evolution, you somehow simplified your life, because and then it doesn't look like.
I agree. And as long as you would only have your Markovian bus, you would be fine with the perfect time, local in time evolution. You don't need to care about the past. As long as, but as soon as you have both a kind of environment, then you cannot play this game anymore.
So this diagram is not either or.
No. So the first part of the talk was either. Now what we want to do is both. That's a good point. I have to find a different kind of artwork to give the idea that we're doing both at the same time. Okay,
it's the same time.
Depending, you can be coupled to an environment which is very fast through certain processes, for example, correlative loss, and through an environment that is slow and maybe describe single particle processes, but which are slow because the density of state of the bus is as a structure, and you cannot just forget its frequency dependence. You cannot make the Markovian approximation. And I give you some example of systems like this one-dimensional wire with a loss. You have a wire, and this wire is a many-body system, for which you can probably not do the Markovian approximation. But for the local loss, the process in which a particle just escapes and doesn't come back anymore, probably for that thing, the Markovian approximation is good. But if you have both in the problem, then you need to find some way to deal with that. And that's what we have been trying to do. But I would say that this is really very open. Okay? Took several decades to develop sophisticated techniques for quantum impurity models, and we are far from being there for this system. So I'll give you 2 or 3 slides with some equation and what we have been using. So one way to deal with that is start to do a diagrammatics, and the kind of philosophy is the following. I know how to solve the Markovian problem, exactly what Misha was saying. I know how to solve the Markovian problem because I know how to diagonalize a Lindbladian. Even for a small system, I can do it even exactly. What I cannot do is to do this together with the non-Markovian bath. So why don't we do some sort of diagrammatic expansion that has been used a lot in condensed matter physics in terms of this non-Markovian bath? And you can do this diagrammatics. You can write down Dyson equation, and this Dyson equation describes the evolution of the super operator that brings your density matrix from time 0 to time t. It contains everything, and it's an equation that is exact, but as any diagrammatic theory, you cannot do much with it. This series of diagrams, of course, need to be the sum, but we can take experience from condensed matter physics and select, do self-consistent diagrammatic resummation. And what we have been using here is what is so-called non-crossing approximation. It's something you use in that system or you use for impurity problem. And we have been extending this to this sort of super operator structure, something that for unitary quantum impurity model has been done for a long time. So this is something rather new, and I think it's pretty promising, but of course, you might want to do other things. So another thing that you can say is saying, look, I don't want to really care about this frequency dependence of the non-Markovian bath. I will reintroduce all the modes of the bath. I will write down this bath in terms of a set of degrees of freedom, and then I will have just one big Lindbladian. It will be very big because if I want to take the thermodynamic limit of my bath, I will have to suffer. But it's a Lindbladian, and I can diagonalize it, and I can look for the spectrum. And this, for certain problems, I will give you an example, is a technique that can work. So you see, this is a sort of reparametrization of this bath spectral function that I usually call delta of omega in terms of a set of bosons or fermions that have parameters that kind of reproduce my spectrum. And I'm basically going from a sort of diagrammatic technique to a sort of Hamiltonian or Lindbladian problem in which I can put this on a computer and diagonalize it. Of course, the price you pay is that you have to truncate the number of levels in the bath.
When you point.
You're right, sorry. But you are here, I can still point for you. What can I say? Anyway, so this is a way of solving this problem with exact diagonalization. Let me also flash another approach that we have developed in collaboration with Lorenzo Rosso, Leonardo Massa, and Fernando Iemini, and I think this is also very, very promising. It's called flow equation, dissipative flow equation. You might have heard of the flow equation method because it's a technique very used for Hamiltonian problems, and it's a sort of iterative diagonalization, sort of RG picture of your Hamiltonian, in our case, of our Lindbladian, and you do a series of infinitesimal transformation. They're not unitary transformation because Lindbladian, again, is an Hermitian operator, but they are transformation that can bring the Lindbladian to a diagonal form. And there is a lot of space there for improvement. There are different kind of generators that you can choose for this this transformation. And we have used that to kind of address this localized impurity problem, finding some nice results and emergence of what is called a strong dissipative state. Again, sort of a lifetime going as 1 over the dissipation, which is this Zeno signal. Okay, so I think I can now enter into the more in the application part. I hope I give you a sort of overview of what kind of system, why we're interested in those, and how those can be solved. And so I will first discuss a very simple sort of benchmark problem, and then go back to this bosonic Anderson impurity that I introduced before. So the benchmark problem is something we can kind of understand easily, and it's a single fermionic level, which can have a 0 or 1 fermion, and there is coupled to a fermionic bath. The fermionic bath is a distribution, a Fermi distribution function at 0 temperature and some density of state. And in addition to that, this would be a standard quantum impurity model. In addition to that, we want to add some local jump operator that describe a variety of processes. You have them over here. in the bottom of the screen, you can have single particle losses, so fermionic losses. You can have pump, and you can have a process that is called dephasing that describes heating, describes the fact that when the level is occupied, you actually can emit quanta into the Markovian bath. And so we solved this problem with this NCA technique that I described, and we saw various things. For example, in the first panel, you see the dynamics of the number of fermions in impurity as a function of the coupling to the bath. You see something rather expected, which make us somehow happy when there is eta is equal to 0, so there is no coupling to the non-Markovian bath. You see a perfect exponential behavior. This is what you expect from linear Markovian system, only exponential sort of approach. When you couple it to the bath, you start to see oscillation and non-Markovian behavior. And we saw also something that we also kind of expect. So this was good to understand that the method was working. When you crank up this dephasing, you sort of increase the effective temperature of the system heat up. And so if you look at the number of fermions as a function of the gate voltage, if you want, you're kind of going toward a state in which the system is always half-filled. You see this yellow line over there becomes flatter and flatter, which is exactly what the temperature will make to you. Your dot would be half-filled. So this was a simple application, and I think for fermions, there is a lot to do, and especially the role of interaction and Kunda physics in this problem is absolutely open. But for today, I want to go back to this bosonic Anderson impurity model that I introduced before, that I will reintroduce now, and that will be the rest of my presentation. So what is a bosonic Anderson impurity model with two-body losses? I have again a sort of an equation of motion of this form. You have an Hamiltonian that describes an impurity. It's a bosonic impurity that can have a certain number of boson in it, and you pay energy U for multiple occupancy. And you have this local Hamiltonian coupled to an environment, to a set of bosons. In addition to that, you have a sort of non-equilibrium processes which inject particles with a rate R times eta, and which is the pump. And instead, the losses are correlative losses, are described by this jump operator will describe two-body losses, and they occur with the rate eta. So the kind of key parameter in this story is the ratio between pump and losses that we call R. Okay? So again, you can think of this as an interesting problem by itself. You can think of it as a sort of toy model to understand lattice problem of boson with correlative losses through dynamic amplification. And this kind of analogy between impurity problems and lattice problem, I will use it in the rest of this talk because I think can be used. So this model was studied in equilibrium. So let me just tell you what people expect for a bosonic impurity coupled to a bath. You can think of it as a sort of model for a static impurity in a DC. So you can think of it as to have two kind of pieces of boson, one very tightly trapped, and the other that describe the impurity, and the other delocalized to describe sort of BC. And as a function of, so you see you have now here it's equilibrium, so you only have the Hamiltonian, and you want to specify the spectral function of the bath, which is this delta omega, and these people with NRG, with numerical renormalization group, draw a phase diagram, a grounded phase diagram for this model as a function of two parameters. One is a sort of chemical potential, is energy, sorry, over there it's written omega naught, but you should read epsilon naught, sorry for that. So it's sort of chemical potential, and as a function of the coupling to the bath, this parameter alpha, the dissipation. And you see a sort of phase diagram that, if you're familiar with sort of Bose-Hubbard physics, can kind of resonate. You have a regime when the coupling to the bath is very large, in which the system, an impurity, is essentially embedded in the DC, and locally the impurity is in a coherent bosonic state. And you have instead a set of lobes where the system is incoherent and the occupancy of the bosons is pinned to almost two integer bounds. Okay, so this is the equilibrium problem, and now what I'm trying to want to discuss is what happened when we actually include this drive, and dissipation. And I will try to show you that many things change, and the physics change quite a lot. And in fact, it changed quite a lot already if you look at the sort of zero-order problem, only the impurity and the Markovian environment. And then I will add the external buff. But already this problem shows some sort of surprising feature that you wouldn't expect in thermal equilibrium. So it turns out this master equation has been around for a long time. This is essentially something that you, depending on the context, you can call it a quantum version of a van der Pol oscillator in other contexts. Many things were known. For example, it's known that so you solve this problem, you find the stationary state. The system, if you truncate the number of boson, has a well-defined stationary state. You look at the densities, the steady state density matrix as a function of the number of boson in the cavity, number of boson in your system, and you see that as a function of the drive, if you increase the drive, you see something funny. The blue line shows a sort of thermal occupancy. Higher bosons number are less likely to occur. Instead, when you increase the drive, you see this red curve are strong drive, you see a non-monotonic behavior. This is called population inversion, meaning that there is a region where having lower occupancy is actually less probable than having higher occupancy, okay? So this population inversion is already something that you don't expect in thermal equilibrium. Thermal equilibrium is Boltzmann, e to the minus beta h, you expect, and the energy scale with the number of boson, you expect that this not to happen. And this is already a signature of the non-equilibrium nature. This was known even analytically, something that we realized that something even more dramatic happens if you look at the spectrum of this single anharmonic oscillator. The spectrum, for me, is a sort of density of state. In more technical language, it's the imaginary part of the retarded Green function. You can call it density of state. And so, if you look at it in a weak drive regime, you see a series of peaks. So these peaks are somehow nothing so surprising. You have essentially a single particle transition between states with n boson and n plus boson. And this line weight, which in equilibrium would be extremely sharp at zero temperature, here are broadened because you have dissipation. This is not so strange. But if you crank up the drive and you go in this regime where the density matrix is inverted, where the population are inverted, you find something that took us a while to sort of convince it was not a mistake. You see what is called a negative density of state at positive frequency. So if you remember your sort of condensed matter physics, so those kind of things are usually satisfy some well-defined sum rules and sign rules. For boson, if you are a positive frequency, the spectral function is positive, and if you are negative frequency, it's negative. It's an odd function of frequency. So what is going on here? This is not a mistake. This is actually the signature that the system is on the verge of emitting emission. So this negative density of state means gain. So what is the density of state? Density of state, you can think of it, is the absorbed power when you send a small light field coupled to your system, and you ask what is the energy rate that the system absorbs at frequency omega. If this quantity is negative, it means that the system is not absorbing, the system is gaining. And so what is actually happening, and in this driven dissipated system is known to happen, an example, of course, is the laser. This is a gain phenomenon. Okay, so this is also very much due to driving dissipation and nonlinearity. Now I can add the non-equilibrium bath, and something interesting we found is that this non-equilibrium bath completely fixes and kind of is able to absorb the energy that the single side is emitting. You see, this plot is again the spectral function as a function of frequency, and now I'm increasing the coupling with the bath. And you see that this region of negative density of state and low frequency gradually disappear. And when the coupling with the bath is large enough, you get back to a well-defined density of state. So this is telling you that the system, due to drive, is on the verge of emission, but the coupling to the bath allows this to this emission to be reduced. And this has important consequences through the MFT. If you think about lattice problem, and this is what we saw in this problem, is that actually this is a mechanism, is a non-equilibrium mechanism for destruction of a sort of non-equilibrium superfluid phase. The fact that due to hopping and coupling to the rest of the system system increases the decoherence. And so you see in this phase diagram, this dashed line, yellow dashed line describes a sort of broken symmetry phase in which would be superfluid, and due to this DMFT correction, this region is shrink. Let me go to the final example that I want to describe. Is again this problem of two particle losses, but now I want to go in this regime that I mentioned before, is the Zeno regime, and is a regime when the two body losses are the biggest energy scale in the problem, or certainly bigger than the hopping. Okay, so let me first of all remind you something. This dissipative process destroys bosons when there are at least two bosons in a given site. So this tells you that when eta is very big, every site which has more than two bosons will be very effectively depleted. So this tells you already that in this regime, the system goes, and this is some result that comes from Sirac group and was also seen in an experiment, goes to a sort of dissipative hardcore regime. Only the 0 and the 1 survive the dissipation. All the other ones decay very quickly. And this is the first fact, this is the first result. But let's think about what kind of effective dynamics this hardcore boson feel. The 0, the vacuum, is still sort of transparent to anything. But the singly occupied boson, of course, is transparent to the two body losses because it's alone, but it can virtually hop to a next neighbor, create a doublon, and disappear. So this process, this virtual process, goes at j square over eta, and it's what is called sort of a Zeno regime. Zeno regime because you increase dissipation, and actually the effective dissipation of the single occupied boson goes down. You see, and it's the exact analog of the Kunda coupling or the antiferromagnetic exchange in the Hubbard model come from the same sort of process. You hop, you create a doublon, but here now you decay, and this gives you a dissipation rather than an interaction that goes at j squared over eta. So this Zeno effect means that the more you are dissipative, the larger is eta, the less actually your system is dissipative. This shows up in a variety of observables, and the most interesting thing probably is the decay. So this system eventually will deplete because if there are no pump, there is only losses, this will deplete, but it will deplete very slowly. And actually, there was a recent paper by Leonardo Davide Rossini and colleagues that actually find out that this depletion is even slower than what mean field theory would tell. So for entering this Zeno regime, what we did, rather than looking at how the system depletes, we actually added a small pump, much smaller than the losses, in such a way that you're still dominated by the 0 and the 1. You still are in a dissipative hardcore regime, but you can get in a genuine steady state. Your long time limit is not the vacuum, but it's a sort of combination between 0 and 1 on each side. And this Zeno scale is there even in this steady state, and it's captured by the MFT. And I think my last slide is just to again come back to this impurity perspective, because this Zeno effect is rather interesting. The MFT captured it through this non-Markovian bath, and so we wanted to look into how exactly this non-Markovian bath managed to give you a Zeno effect. So we use this trick of kind of unfold the bath into a set of harmonic bosons, and we diagonalize exactly this problem. And the nice thing of this is that then you can look inside the bath. You can diagonalize and look at the reduced density matrix on each side of the bath. We found something somehow surprising. Of all the levels in the system, in fact, only one bath site is essentially populated in this Zeno regime. All the rest is almost empty. You can see it in this plot. The scale of the third site is essentially 0. So it looks like the Zeno effect can be described very effectively by a sort of Diner Bose-Hubbard problem. and that's something we want to understand better. The Zeno effect appear here in the lifetime of this only site that remains. Okay, I think I am more or less the time. I hope I didn't go too fast. Let me wrap up. So I hope I motivated at least a little bit of interest toward this kind of hybrid impurity problems in which you have two kind of environments: a Markovian one, which could be maybe interacting correlated dissipative processes, and a non-Markovian one. And this requires new methods to kind of deal with these two kind of environments. I focused mostly on impurity, bosonic impurity model and the Zeno regime, but there are many open questions involving fermionic impurities, Kunda effect, interliquid, and so on. So let me also acknowledge the people that did this work. So this was done by Orazio Scarlatella when he was college with me, and by a student and Massimo Capone, and collaboration with many other people that are acknowledged. And let me also thank you for listening.
Yes. Christoph, you want first?
So, hello Paris, hello Saclay. Here's Innsbruck. Hello. Thanks for the nice talk. I have a question on the last part,
Sure.
on the Zeno effect part, because we've actually been looking into this over quite some years. In our experiments, and I have to say, unfortunately, our data was never conclusive, whether it was with atoms or with molecules. So we've been looking at this in lattices, or even also in 1D, where motion is along only one direction. And the problem, I think, that comes in, that the separation of energy of rates is not so good, in the sense that we, apart from having a J, tunneling or hopping rate, there is certainly there is the loss rate. In our case, it's actually, we looked at three-body processes mostly, so we worked in the ground set, so it's not two-body but three-body. But it turns out that certainly there is the band gap to the next higher band, and that's not too far away. So so that's why we were always not sure whether we see anything or not. It was not really conclusive. So we am for sure when you then have very strong losses, you start in to mix in the higher bands. So I'm just saying this as also as a motivation that perhaps one should look at, in this case,
including higher bands,
at least the next band or so. Yeah,
I see.
And perhaps just one comment on the paper from the Rempe group. I have to look at it one more time again. Also, I haven't done for some while, but I think that when we concluded long time ago that the data was not conclusive. In particular, one thing is for sure wrong. You don't expect the number of particles to fall to zero, because they have actually isolated tubes, thousands of them. So you expect the number to go down to when you have one particle left per tube, then so then nothing can happen anymore.
So you are saying that these higher tubes can sort of provide another reservoir for which
just trivially, that when the decay goes down, when you don't expect it to go to zero, to a few thousand probably, depends on how many tubes you have, and in the end whether you have then, when you have two particles, if it's two-body loss, two particles, the last two particles might kick out each other, but when you have three particles, one particle probably will stay.
I see.
So whether you have initially even or odd number of particles, for sure there will be probably a few thousand, perhaps 2,000 tubes that still have a single atom left at the end. So that was not taken into account trivially, apparently, in the analysis. So we were never so sure whether when we should reanalyze their data. I'm just saying this in view of our problems that we've had with similar systems. Was never really conclusive.
When you say conclusive, you mean sorry, apologies. Hello? Yeah.
I turn off my sound for a second.
Yeah. Okay, sorry. No, I was wondering, when you say conclusive, you mean you wouldn't clearly see this non-monotonic behavior with the three-body loss rate, or what exactly? Or you wouldn't see the power law decay that this people was claiming, or?
Yes. So we expect that the Zeno effect helps, yeah. And I'm still optimistic that perhaps we find a regime where it helps, that we effectively reduce the loss rate via the Zeno effect. And and it appeared, at least in our case, that it never did so.
Okay.
Yeah. So it's and it shouldn't. I have to admit, this is still work we have to do to really better quantify the loss rates and really show data, and then perhaps really see at how the decay happens and what really get more be a bit more quantitative on that. And we've done this, and actually I'm saying this now without having data in front of me exactly not right now, but we've done it with atoms and also with molecules. And we thought that in 1D, actually the Giller group claimed also to see a Zeno effect for losses for molecules in the lattice. Yeah. So I'm just saying it's difficult, and I think
but that's
partially it's because of the higher bands, and that we are not able to separate or to separate these rates enough. Yeah.
Okay, thank you.
Anyways, but it's very interesting, and it's perhaps something really worthwhile to revisit also from the experimental point of view. Yeah.
Got a question also? Can I ask one? Marco, can you hear me?
Hello. Yeah. Hello, guys.
Hey, how are you? So great talk. Thank you. So, just kind of on a technical level, what you're actually doing here is you're doing the standard NCA, but you're replacing the local propagator with the exact solution, the exact diagonalization solution of the local Lindblad problem.
So yeah, we are doing NCA for the super operator, for the super propagator, if you want.
Yeah, the super propagator. So then, does that actually, like, is the only approximation then just the NCA? Like, if you were to continue the standard hierarchy, would that be exact at higher orders?
Yeah. We wrote down the entire hybridization expansion, and maybe this could be even sampled with the good old diagrammatic Monte Carlo. But of course, the truncation, we did the truncation at the NCA level. Then you can go. The price to pay is that this object becomes n square, where n is the size of the Hilbert space, rather than because it's a super operator. So it's but okay, this is the price to pay. Yeah.
But that's not much of a price, actually, right?
No. I mean,
these propagator expansions at the density matrix level, anyway. Yeah, so that might be relatively easy for us to do at higher orders. So if you think that's interesting, then
yeah, definitely. I mean, for fermions as well. Yeah, I definitely try to talk. Yeah.
Okay, thank you.
Thank you.
Hi.
There is ciao Leonardo. There is.
Hey, ciao Marco.
Leonardo.
There is a question by Christophe.
Okay, so I will ask later.
It's okay.
Well, go ahead, Leonardo. Go ahead.
On screen. Go.
Okay, thank you very much, Christophe. So, hi, Marco. I have a question concerning the part where you discussed your dynamic midfield theory for two-body losses and pump.
Yes.
And so this phase where you have, I guess it's some form of spontaneous symmetry breaking, right? Where the expectation value of the A operator is different from zero. So if I imagine I'm a numerical guy and I do simulation with some quantum trajectories, right? So what should I look at some time correlations of my quantum trajectory, or it's a spatial correlation that you're signaling?
I would say you can see locally in the time resolved correlation function of the system. But if you have a finite size, It's still a Q equal to 0 mode that orders. It's just that it orders in frequency, but it's still a Q equals 0 mode. So you want to look at also a long distance correlation. If you have a finite size system, you cannot break the symmetry. You have to look for correlation function.
Right.
So you will have to look for something a long distance and in time. It's a space-time order, if you want.
Okay. Thank you.
So now I can ask my question. Maybe I ask it with this microphone. On the theoretical side, do you expect a significant difference between the two-body loss that you have described here and three-body losses on site? Because I guess, for a BEC, three-body losses have, are different. You have the bosonic symmetry or not? So is this just a...
I think there will be. It's a very good question. We haven't really looked too much into three-body losses. I know that if you include them, there were various works. I think the kind of symmetry breaking you can have becomes way more rich. So I think so. But the good thing is that the approach we have developed doesn't really care whether it's 2 or 3. So we can deal with 2, we can deal with 3 at not very different cost. So that was the whole idea.
Would be interesting because, for cold gases, very often it's three-body losses that comes in, unless you do what was done at Collège de France, by the way, by Fabrice, where you put light plus two-body losses.
Otherwise, the natural,
But naturally, you get three-body loss in many cases, not always, but in many cases.
Thank you.
Any other question from online, from auditorium?
Can I ask a question, please?
Go.
Could you please detail, you have mentioned that the Bose-Anderson impurity model has an analytically known stationary state. Could you please detail on this?
Sorry. Well, do you see my screen?
No.
No. Okay. So just let me see if I can establish quickly, but I don't think so. The statement was that the bosonic impurity without the bath, so I'm talking about single bosonic mode with interaction and those kind of dissipative processes that I described, two-body losses and single particle pump, this as a steady state density matrix that is known. It doesn't include all the degrees of freedom of the bath. So I'm not saying, and I don't know if that's the case, that would be very interesting. But I'm not saying that the full Hamiltonian problem with the bath, non-Markovian bath, and the rest has a well-known steady state solution. I'm saying that the back in the 70s, Mark Wickman and probably others before, on a closed form expression for this interacting anharmonic oscillator with pump and two-body loss, which is already remarkable because it's still sort of an interacting function problem with an infinite Hilbert space. Because, but that's what it is.
Yeah. Thank you.
Any other questions? Okay, in that case, I stop recording of this session.